Welcome back to another video with us here at LMD and STEM Academy. In this video, we will be working through the June 2018 Unit 2, Paper 2, and we will be working on question 2. Specifically, Part A was a question on gravimetric analysis. So it says that gravimetric analyses rely on the final determination of weight as a means of quantifying an analyte. Okay? So we're asked now to describe the function of each of the following pieces of apparatus used in gravimetric analysis. So the first one we're going to look at is a suction flask. And the suction flask is used to filter off precipitates under vacuum, right? Now the suction funnel is the next one, and that is used for filtration under vacuum. And in fact, the sintered glass crucible is generally placed in here, okay, in your suction funnel. Now the silica crucible is used for heating the solid precipitate within it to very high temperatures. In fact, can go up to 100 degrees Celsius, and that's for drying the precipitate while we would be heating, okay? All right, so now the sintered glass crucible, that's used for heating, again, the solid precipitate that is within it up to high temperature, but now we can only get up to 400 degrees C when we're using the sintered glass crucible, okay? That's the limit. That's the upper limit of it. So if we need to heat something to a very high temperature, we're going to be better off using the silica crucible because that one can go up to 100 degrees C. So just keep that difference between these two pieces in mind, but they're both, you know, these crucibles that we're heating things in, we're drying our precipitate in, okay? All right, so now the final one is oven/furnaces. So the ovens or the furnaces are going to be used for drying your reagents that you're going to be using for this precipitation. So you can dry the reagents and the precipitates, and you can use it to dry and condition any glassware that you're going to be using for these gravimetric analyses, okay? All right, and so we're ready to move on now. And so part B was a calculation now based on gravimetric analysis. And so it reads that a sample of impure potassium chloride, KCl, of mass 0.450 grams was dissolved in water and treated with an excess of silver nitrate. A precipitate of silver chloride of mass 0.8402 grams of mass was obtained. Okay? And so let's see what's needed for us here. But before we even get into anything else, I think the strategy here, whenever you're given these numbers and these words, right? What you're going to need to do first of all is write a balanced equation for the precipitation reaction, because this is a precipitation that's going on here, okay? So we have impure KCl and we dissolve that in water. So what we're going to get is aqueous KCl. And then to that, we're going to add an excess of silver nitrate. So that's in the aqueous phase. And then from that, we're going to form the silver chloride precipitate. And of course, you know, we're going to get some potassium nitrate in the aqueous state as well, because this precipitation reaction is really just a displacement that's going on, right? Where the silver is displacing the potassium to form AgCl solid, okay? So we have to write our balance equation for the precipitation. That way we can put these words and numbers in equation form ultimately, because when we have our balance equation, we know mole ratios, right? So now we're going to have a mathematical relationship between the KCl and the AgCl. So that's what we have here. So from the balance equation, we know that the relationship then between KCl is that 1 mole of KCl is going to produce 1 mole of AgCl. So everything is a 1 to 1 to 1 to 1. So if I have a mole of KCl, I'm going to get 1 mole of AgCl, okay? Because all the ions that end up in the AgCl have to come from the KCl. All right, so this is our basis. This is how we just kind of break down everything that's written here into an equation form and numerical form. So now we're ready to work. Let's see what's being asked of us. The first thing we're being asked to do is to calculate the number of moles of silver chloride produced, right? So we need to know, let me just get my pencil here. We are trying to find the moles of this that was produced, right? So that's what we're trying to find. So if we want to find number of moles, right, and we know the mass of the precipitate of silver chloride had a mass of 0.8402 grams. So we know the mass of the precipitate, right? And we need moles. So what are we going to do? Here's our formula. Moles of AgCl produced is going to be the mass of AgCl precipitate. So that divided by the molar mass of AgCl. So moles is equal to mass divided by molar mass. Our mass of the precipitate was 0.8402 grams. So we put that here. And then we're going to divide that by the molar mass of AgCl. And that's just this number here. And so we're going to come out with a number of moles of silver chloride produced. Okay? And so now we know that we made 5.86 times 10 to the minus 3 moles of silver chloride. So I'm going to just go ahead and just jot that number down here beneath the silver chloride. I'm just going to put it here. 5.86 times 10 to the minus 3 moles, okay? That's how many moles of silver chloride were produced when we did this precipitation reaction. All right, so let's keep moving forward now. So going right ahead. All right, so now we're being asked to find the number of moles of KCl that's present in the sample. So number of moles of KCl present in the sample. So from the balance equation up here, we knew that everything was a 1-to-1. KCl to AgCl was a 1-to-1 mole ratio. So if it was that 5.86 times 10 to the minus 3 moles of silver chloride were produced, then that means that 5.86 times 10 to the minus 3 moles of KCl were present, right? It's a 1-to-1. So if I made this much AgCl, I must have had that exact same amount of KCl because the KCl is where this came from, okay? So I'm just going to jot that down here. That's also going to be 5.86 times 10 to the minus 3 moles. Okay? So that's literally what it means. 1-to-1. Okay? All right. So let us move on now. See what else is being asked of us. So this was part 2. So let's see what part 3 is all about. Part 3 now says that we have to calculate the percentage of KCl present in the sample, right? So a while ago, we got the moles of KCl, right? A while ago, we got the moles of KCl. So that was our moles of KCl. And now they want us to find the percentage of KCl that's present in the sample. And that percentage of KCl, just to be very specific, it is a percentage by mass, okay? It's a percentage by mass of KCl that we're being asked to find. So the percentage of KCl in the sample then is going to be the mass of pure KCl that was in the sample divided by the total mass of the impure sample that contained KCl, right? So this requires a little bit of just thinking to just realize what's going on, right? It's a sample of impure potassium chloride that we got that weighed this amount. The impure sample, so that sample had KCl in there plus impurities. So that's not all KCl. That's very important to realize off the bat that there's KCl in there and some impurities. So that's the total mass of the impure sample, right? This number here. And in order to find the percentage of KCl in the sample, then we're going to need to find out the mass of pure KCl in the sample, right? We're going to need to find that. How are we going to find that mass? Well, we know the moles. We know the moles of pure KCl in the sample. Okay, we just calculated that. So because we know the moles of pure KCl in the sample, we can then find mass. Okay, so how do we get from moles to mass? We are going to do mass. We're going to do the moles of KCl in the sample that we just got times the molar mass, okay? So the mass of pure KCl in the sample is going to be the moles of KCl in the sample times the molar mass of KCl. The moles of KCl in the sample was from up here. It's 5.86 times 10 to the minus 3 moles. We're going to multiply that by the molar mass of KCl, and we come out with a value of 0.4366 grams. Okay? So that's how much, right, pure KCl was in this sample that had the impurities. Okay? So the percentage then of KCl that was in this is what we're finding. And so let's put that here. So here's this now. So we're gonna literally take this mass. In fact, I rounded it off to 0.437 grams to be consistent with this one where we only had 3 decimal places. So I rounded that off to 0.437 grams. And that's what I'm gonna now put what here, right? And then I'm gonna put the total here. Right, so right here is where I'm going to put the total. So this guy goes here, and then this goes there, right? Because that's the mass of pure KCl. So now, here it is, 0.437 grams divided by 0.450 grams times 100, that's the percentage, and that is 97.11%, okay? So in this sample, guys, it turned out that we had 97.11% of KCl. Okay, so everything else would have been impurities. Everything else would have been impurities that made up that sample, right? And so that's how, this is one of the most powerful ways in which we can use gravimetric analysis to really figure out if you're given a sample that has impurities, how much of it was actually pure, your pure compound, okay? And so with that, let's move on to the other part of this question. So this was part 3. So let's move on to see what else there is here. All right, so we're moving on to part C. Part C says, state one example of the use of gravimetric analysis in quality control. So gravimetric analysis has a vast array of uses in quality control because as we just saw, right, we can have a specific sample and then we can do a precipitation and figure out, right, we can work backwards and figure out, okay, how much of the actual pure substance was in it. So we can use it for quality control that way to figure out the amounts of specific elements or compounds that are present in a given sample. And so here is one example that I would have written here. I would have written that it can be used to determine the amount of certain elements, such as phosphorus in fertilizers. That's a very specific application, and that's what they want, right? So I wrote that one for my first one. That's what I would have submitted, but you could have also written, it can be used to determine the concentration of chloride ions that's present in our water supply, right? Or it can be used to monitor the concentration of gases like sulfur dioxide in air and in wine and in fruit drinks. So remember, the thing here that we'll be doing in each of these cases is that we'll be making an insoluble precipitate, just as we did in the calculation earlier. We made an insoluble precipitate of silver chloride, and then we were able to back calculate to find out how much was in the original sample. So in all of these 3 cases, you're making insoluble precipitates. That's what the reaction would be that you'd be performing. You're making insoluble precipitates that you can then work backward to find out, okay, where did all of this come from? How much was actually present, okay? All right, and so with that, we're gonna move on now to the other question. Definitely give this video a like, subscribe to the channel, and if you look on the left here, you'll see the next video up. And if you look on the right here, you'll find our Module 2 playlist with tons of interesting content that will be helpful in getting you prepared for your exam. So, thanks for watching, and we'll see you in our next video.